So inverse variation, we said the equation is y equals a over x. Okay. And I'm going to switch it over to rational function, which is really what chapter 7 is all about. All the things we can do with rational functions. You know, last chapter was all the things we could do with exponential and log functions. What math word is in the word rational? Math word. Ratio.
Fun.
Oh yeah, and fun. That is a good math word. Okay, I like that. Okay. Ratio is the math word that I'm looking for. What do ratios look like?
Number with like the 2 dots in the middle.
Yes, sometimes we see them with the number with the 2 dots in the middle, like 2:3, which is a 2-to-3 ratio. But like later on, you start talking about ratios more as what Sierra said, which is a fraction.
Oh, yeah.
Yeah, it's just a relationship between two numbers, right? So either one would work. But rational generally means fraction. And so rational functions, here's how they're commonly written like in a math textbook. We call it f of x because it's a function, so we're using our function notation, equals, and then we say p of x divided by q of x. So we're creating a fraction, right? Numerator and a denominator. Well, in the numerator and the denominator, I put more function notations. I called them p and q. Okay. So what it's saying is this is a function that's made up of a fraction of 2 other functions. So there's a function in the numerator and there's a function in the denominator. It just so happens that in order to be considered a rational function, p of x and q of x have to be polynomials. I'm going to move the slide up here in just a second. Polynomials. So again, I'm writing a function in terms of 2 other functions, p of x and q of x, that are being divided, okay, because they look like a fraction. And those other functions, p of x and q of x, have to be polynomials. Okay, so let's just randomly make up our own rational function. We'll say f of x equals, let's put a numerator up here. Can someone give me an example of a polynomial? 2x? Okay. That's a linear polynomial.
It works.
Yes. What's another example of a polynomial? X plus 3. Another linear polynomial. Now we have 2 terms. Okay. This could be a rational function. This could actually be a rational function that I asked you to graph today. So I consider this one to be a simple rational function. Now, you guys chose linear polynomials, but do you remember like polynomials, you can have all different kinds of exponents? Yeah, so quadratics. Later on in Algebra 3 or pre-calculus, wherever you're going next, you will re-study rational functions, and you're going to see something like that might be more complicated, like f of x equals x squared plus 4x plus 3 divided by x squared minus 5x plus 6. Okay, so they can look more complicated. We're going to be sticking with simple ones because we're just like doing introductory. But next year you'll be asked to do ones with bigger polynomials in the numerator and the denominator. Okay? So basically it's like a fraction where you would likely have x's in the numerator and the denominator, although we'll see a case where we don't have x's in the numerator. Okay, so that's basically what a rational function is. And then I want to go back and like do that tie-in of why did we ever talk about inverse functions? How are these 2 things similar?
Well, f of x is a nice way to write y.
F of x is a fancy way to write y, and what do you see on the other side? A fraction, right? I mean, this y equals a over x, this inverse variation, is really just a rational function. So inverse variation is one example, and I'm going to put a qualifier here, simple. rational function. We're going to see on our next slide, I'm going to do a parent graph because it's like, okay, well, what are these simple rational functions going to look like? Like, what shape are they going to be? You know, quadratics were parabolas, square roots was the little sideways parabola, half of it. You know, exponential had the asymptote and went up like a J. So it's like, what is the shape going to be? Well, we're actually going to use inverse variation because it's really simple. It doesn't have a lot of stuff going on, and that's going to represent our parent graph. So that's kind of the tie-in of why did we ever talk about inverse variation. All right, let's move on to the graphing part. You can name this as the parent graph for rational functions, meaning other rational functions that you will graph, and I should clarify, simple rational functions, will share a similar shape to this parent graph. And I took my y equals a over x and I made a very simple 1. So we're going to graph y equals 1 over x. Now I've preloaded a table of values here. We could really pick whatever we want, but I chose some different x's that will give us some interesting points on our graph and get a clearer idea of what's actually happening on the graph. So we'll start by just plugging in those different x values. If x is negative 10, and I plug it into the denominator here, what's my output? Negative 1/10. Cool. If x is negative 5, then my output is negative 1/5. And if x is negative 2, my output is negative 1/2. Now, what if I put in negative 1/2 in the denominator? How'd you get negative 2?
Because you know it's going to be like, I just think of like the inverse here, multiply by 2.
Yeah, if you're doing y equals 1 divided by the fraction negative 1/2, you're really multiplying by its reciprocal. So this is 1 times negative 2 over 1, which of course is negative 2. So what happens when you put negative 1/8 in?
You're going to get negative 8.
Negative 8.
I'll break the silence.
Thank you, TJ.
No problem.
Okay. What if we put 0 in? 1 divided by 0 is 0. False. 1 divided by 0 is undefined. We cannot and have not ever divided by 0. So there's another restriction to our domain that you already knew. Okay. So this is undefined. I'm just going to put an x there. It just means like I don't have a point to plot at x equals 0. I'm just going to skip over it. And then you can fill in the rest of the table pretty easily, right? I've got 1/8, 1/2, 2, and 10. So we'll get 8, 2, and 1/2, 1/10. Now, because we've never graphed a rational function before, I just was like, let's do a whole bunch of points and like figure out what the graph is going to look like, right? In any math class, in a worst case scenario, you have no idea what your graph looks like. If you have the time on a quiz or a test, make a big table of values and plot as many points as you can. Okay, well let's plot points. So I gotta make a big coordinate plane because I gotta get from negative 10 to 10 on my x's. I'm running into my table over there. And then I gotta get all the way down to negative 8 on my y's. And positive 8. Okay, let's plot some points. First ordered pair. Negative 10, negative 1/10. So it means go left negative 10, and then down 1/10. That's just a little bit. Really close to the x-axis, right? I've run into my table over there, so I apologize. Then -5, -1/5. So I go 5 to the left, and then I go down a fifth, which isn't very much more, is it? It's also really close to the x-axis, -0.2 if you check in your calculator. Okay. At -2, I'm at -1/2, so that's getting a little bit better. I'm finally moving away from the x-axis. At -1/2, so if I go left a half, then I get to go down 2. Yep. Sort of bypassing the origin. That's a good way to say it. Curving away from the origin. And then my last point over here on the left is -1/8, -8. So -1/8, if you'll agree with me, like you're just barely going to the left. And then you got to go down 8. 1, 2, 3, 4, 5, 6, 7, 8. So go down 8, and then I'm like right next to the y-axis. But the other points, the positives, 1/8, 8, 1/2, 2, 2, 1/2, and 10, 1/10, something out there. So we kind of have a graph, but it's in like 2 different sections of our coordinate plane. And because we couldn't make any value here at x = 0, there's no connector, so we actually have 2 different pieces of our graph. Can you kind of imagine what's happening? If I put in more and more negative numbers, like let's say I put in -100, then my output is 1 over -100, which is really, really close to 0, but still not there. So this side is going to be trapped under the x-axis, and as I move closer to the y-axis, then my numbers just start plummeting. Like what if I put in -1 over 100? Then I'll get out -100. It's got to be all the way down 100. Okay. So I've got this piece right here, and then up here I have a similar piece, but it's trapped between the x and the y-axis again. So what are the x and the y-axis going to be for us? Asymptotes. Yes. Go ahead and draw in those asymptotes. I know a lot of people like in logs and exponents, maybe it was like our first time with asymptotes, so we were a little unsure. But you should start drawing your asymptotes in the graph because they're there to help keep your graph in the right spot. Okay. So draw your asymptotes in. And I'll go ahead and label them too, I guess. I have a vertical asymptote. Where's my vertical asymptote?
0.
How do I write that?
Y.
X = 0. Vertical is x equals. And horizontal is
Y.
y = 0. Excellent. What can you say for the domain then of this rational function? Inverse variation. What kind of x's work?
Greater than 0.
Greater than 0, less than 0, so any x that's
Not 0.
not 0. So we can simply write x is not equal to 0. And what will we say for the ranges?
Y.
Is it all real numbers?
No.
No, because of the horizontal asymptote.
Oh, yeah.
So we'll say y's that are not equal to 0. Why don't you ever get out a y that's 0? What's preventing that from happening?
Wait, but could you get a
Because
Y
the
that's
undefined.
greater than 1 right now? You couldn't get a Y that's greater than 1 right now, right? Well, not.
Yeah, if you put in fractions.
Oh.
Why don't we ever get 0 out for an output? If our equation is y = 1 over x.
So you can't divide by 2.
Well, dividing by 0 is the thing that prevents our domain. But why is it that y is never equal to 0 in that fraction? if I have 1 of something, do I have something? Yes. So notice my numerator is a fixed constant of 1. It doesn't matter what I put in the denominator. 1 million. 1 out of 1 million. Is that nothing? No, that's something. 1 out of 1 billion. That's not nothing. So, like, if your numerator is that 1, we saw this with exponentials. Like, there's no way we're ever going to get to 0 because 1 in the numerator is always something, not nothing. Does that make sense? Okay, so that's why the range cannot equal 0. Have you seen that graph before? I think maybe in Algebra 1, at the very end of the year, it's possible you looked at rational functions. It has asymptotes, and then these pieces are called branches, so you'll hear me refer to them as a branch. Like you need to figure out where your branch is. And the shape of a simple rational function is called a hyperbola. Not a hyperbole. It's an exaggeration or whatever in English. But a hyperbola. Now, remember on that previous slide when we made up our own rational function? Ours worked out to be simple, so it would fit this. But then I made that one that was like more complicated with the quadratics. Those may not necessarily look like this. Like later on in Algebra 3 and Precalculus, you can have rational functions that have more than one vertical asymptote. You can have rational functions that have things called holes in them, where there's literally just a point that is open in the graph. So there's a lot more weird things that can happen, but we're going to stick with the simple ones. So ours will have a vertical asymptote and a horizontal asymptote. Okay, so here's what you need to know going forward for you to be able to graph all rational functions. There are 2 forms you're going to see. One form has your old friends A, H, and K in it. So we could call that like a transformational form. And we could graph it by transformations. Like A is vertical stretch, H moves right or left, K moves up or down. But because we have this second form with the A, B, C's, and D's, I'm going to give us like one method for graphing. So we're not doing one transformational and one some other way. We're going to do them both the same way, but just have rules for one or the other. So you should be able to recognize which form it is. Notice that the A, H, and K form is more like our inverse variation. It has a constant in the numerator, no x. Okay. Whereas this version has x's in the numerator and the denominator. Okay, so that's kind of how you can tell the difference between them. The one that you guys gave me, like 2x over, what did you guys say, x plus 3 or something like that, that would be this version because you had an x in the numerator and an x in the denominator. They're both linear. Okay, depending on the form, you're going to follow these steps. Step 1, find the vertical asymptote. I'm going to call it VA because we'll have a VA and an HA in the same graph now. So I'm going to say vertical asymptote, horizontal asymptote, VA, HA. Well, the vertical asymptote is the whole issue with the domain, that you can't divide by 0. So if you want to find your vertical asymptote, just set your denominator equal to 0, and there you have it. And these will carry over even into like general rational functions. Like that will be true of how you find vertical asymptotes then. Step 2 is kind of like the crossroads. Depends on which form you have. You're going to find a horizontal asymptote. If you have the form with A, H, and K's, your horizontal asymptote is at y equals K. Because think about it, that K is your vertical shifting. It moves your graph up and down. And remember, like with our exponential functions, we had horizontal asymptotes. If we moved our exponential function up 3, then our horizontal asymptote also went up 3. So that's going to be true for rational functions as well. The yellow box is how you'll find your horizontal asymptote if you have the form ABCD. If you have the form ABCD, then we say that the horizontal asymptote is at y equals A over C. Now when I say A over C, these are the ratio of the leading coefficients, the LCs. So notice that A and C are the ones in front of X's. So it's not necessarily like I could rewrite my equation so that like it was like 3 plus 2x, but then A is still 2 because it's in front of X. This is the one you guys gave me before? One of them. I don't know what it was. Okay, I want to talk about the yellow box. Okay, so why does it work out that the horizontal asymptote is y equals A over C? So this one that you guys gave me earlier, 2x over x plus 3, this is an example of the ax plus b over cx plus d. So I'm going to pick a really crazy x. What if x is equal to 1 million? If x is equal to 1 million, then y is equal to, or f of x is equal to 2 million over 1 million. Yeah, 1 million. 1,000,003. Now, if let's say we became a millionaire, so we had $1 million, would $3 really feel different than a million? 1,000,003 versus 1 million. Did you notice that? No. So like that 3 is like so small at this point that my x is so big that it doesn't really matter. Okay. And so what's this 2 million over 1,000,003 really close to? It's really close to 2. 2 over 1. Is it 2? No, but it's approaching 2. So your horizontal asymptote is going to be that ratio of the leading coefficient, 2 over 1. These like plus and minus numbers, when you go way far out, they don't matter. Okay? And you'll never actually get there because you do have plus or minus something small. Okay? But this will be the horizontal asymptote. That kind of like number sense wise should make sense to you, why we could just say it's the leading coefficient. Okay. And then the last thing is we just need some extra points in order to be able to graph. Okay, I do think I'm going to add on here for the extra points. I think your quiz and tests say at least 4. So I would practice that on your homework, like get me 4 points to sketch the branches. Let's do a couple of examples, one in each form. Okay, here's my first example. Y equals 2 over x plus 4 minus 5. All simple rational functions will have a horizontal and a vertical asymptote. So that's usually where I start. Step 1, find my vertical asymptote. Set my denominator equal to 0. X plus 4 equals 0, therefore my vertical asymptote is at x equals -4. I can go ahead and draw in a vertical asymptote right there. Next step, find my horizontal asymptote. To decide your horizontal asymptote, you have to look at the form. Is this the form with A, H, and K, or A, B, C, D's? This is the A, H, and K, and then when it's A, H, and K, your horizontal asymptote is Y equals K. So we'll say Y equals -5. Cool. So we should go down 5. Okay, now think about this in terms of left, right, up, down shifts. It's like I took my old origin right here at 0, 0, and I just moved it left 4 and down 5. And now I have like a new set of quadrants. Okay. My branches are either going to be top right, bottom left, or they could end up top left, bottom right. They're going to be catty corner from each other. Okay. In order to decide where my branches are, I'm going to pick some x and y values. So what's an x you want to put in? What's that? -1. Okay, 2 over -1 plus 4, that's 2 over 3, minus 5. 2/3 minus 5 is -4 and 1/3. Okay, plot that point. Left 1, down 4 and 1/3. So I'll use blue. Okay, give me another x.
1.
Can I ask you this? Can you look at the equation and, like, you have to put it into your denominator? Is there an x that would make for, like, kind of a nice number in your denominator?
2. So you get
Okay, a third isn't really a nice number to me. -2, because then -2 plus 4 would be 2, and 2 over 2 is 1. Okay, so let's try that, -2. Not that you couldn't do the other ones you suggested, but some of you might like to think smarter, not harder. So put -2 in. So we said 1 minus 5 will be -4. So it's going up a little bit. Well, we kind of know where that branch is, don't we? It's in this top left section. It's going to be approaching my asymptote here and here. Got 2 points over there. I kind of know what's happening.
So,
Can you give me some points on the other branch? Yeah.
Since it's like 4 points, but I only need like 2 in that.
2 on the right and 2 on the left. Yeah,
Okay.
that's what I'm looking for, really. To kind of even it out and just like verify. That way, if you make a calculation mistake, you know that you need to look at it a little bit longer. Yes, ma'am? 4 and 1/3. I have a 1 up at the top. My marker got a little messy there. I'm sorry. Okay, what's an x we could use to get on the other side of that asymptote? -5. And think about it. -5 is going to be a nice number because what happens when we put -5 in? -5 plus 4 is -1. 2 over -1 is -2. -2 minus 5 is -7. So that's a nice one. So I'm going to go left 5 and down 7. That's down. Something like this. Sure, let's do -6. It doesn't really matter. Even if you get fractions, like, we're not scared of fractions. Oh, yeah, this one's nice, though, isn't it? -6 plus 4 is -2. 2 divided by -2 is -1. -1 minus 5 is -6. So that's a good one to choose. So now we're up here. Okay, so now that just kind of confirms what I thought, right? You got your branches. What would we say for domain? X's that are not equal equal to -4. It could be anything except -4. Doesn't matter. And what would we say for range? Y is
It's not equal to -5.
not equal to -5. It can be anything but -5. So notice, like when you're doing your homework, the vertical asymptote should be the same number in your domain, and the horizontal asymptote should be the same number in your range. Okay. Anybody got any questions for me? Okay, I want to do one more, so we got one with the ABCDs. Okay, so you're ready to go for your homework. So we're going to do 3x minus 4 over 4x plus 1. Okay, step 1. Set your denominator equal to 0. 4x plus 1 equals 0. X equals -1/4. Is it okay that your asymptote be located at a fraction value?
Yes.
Sure. So -1/4 just means go left a little bit, right? Don't overthink it. Okay. Horizontal asymptote. Is this AHK or ABCD?
ABCD.
ABCD, so the horizontal asymptote is y equals A over C. What's your A? 3. What's your B? Or sorry, C? 4. So y equals 3 over 4. Remember, it's just the leading coefficients to your x's. 3 over 4.
How do you know what ABCD?
A, B, C, D. That's earlier in the notes. But they just go in alphabetical order. Start at the top. A, B, C.
How do you know if it's ABCD or HFK?
Oh, the form. Yeah, also in the notes. I'll go back to that slide so you can see it a little bit. Okay, let's see. Figure out where your branches are. We gotta get some points. What do you want to plug in for x? Oops. What could be easy to plug in? 1 would be pretty easy to plug in, wouldn't it?
Yes.
Because then that's just 3 minus 4, which is -1, and 4 plus 1, which is 5. So 1 and -1/5. Anything else easy on that side? My favorite one is
You say?
0. Plug in 0, you just get -4 over 1. -4 over 1 is just -4. Notice I don't even take the time to like simplify my fractions because I don't really care. I just need to get my point in the right spot.
Are we going to be able to use a calculator?
Yes. Got my one branch. Now I need to get some points on the other side. What might you use on the other side of your vertical asymptote? X equals -1, sure. Okay, so that'd be -3 minus 4 is -7. And -4 plus 1 is -3. Okay, I don't even care what -7/3 is. All I need to know is that this is a little bit more than 2, right? And it would be positive. It's like 2 1/3. Okay. So that means go left 1 and go up 2 1/3. And then I'll just pick like -2. So that would be what? -10 over -7. So that's a little bit more than 1. And that confirms my graph. Okay. Because you're working with a rational function, something made up of a numerator and a denominator, you're likely going to get fraction answers. So don't be like freaking out when the numbers for y aren't always nice. They won't be. It's okay. Domain will be all x's except -1/4. And range will be all y's except 3/4. Does anybody have any questions for me about that example?
Oh, man. Thank you. Great.
Okay, so for the next couple of days, we're going to be working on this section. Tomorrow, we are going to do a little bit of algebra with the equations. Can we rewrite from one form to the other? But then we'll review on Thursday and we'll quiz. That should say, it must have got rubbed off 7.1 to 7.2. So your quiz is only over these first two sections. So you'll have some time to get graphs figured out, but please work on your homework assignment tonight.